Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to look at our last of our major cases of compression and expansion before we kind of move on to reactive systems. And that's going to be adiabaticity. So this is going to be the idea of looking at systems where we don't allow heat to enter or exit the system. So we brought this idea up a little bit with the Joule-Thomson of how can I go ahead and compress and expand a system under adiabatic conditions. And we'll notice that this will be a little bit non-intuitive with some of the details. So let's go ahead and dive right on in. So we can look at our similar compression and expansion of a fluid in an insulated adiabatic container. So the major idea here is that if I'm working at a piston with an insulated surroundings, this means that I can prevent the heat transfer from going across the boundaries, or it's adiabatic. Again, no heat. That means the only way we're really going to see energy entering or exiting the system is going to be as work. So if we're looking at the change in internal energy, we've previously said that internal energy can go ahead and change with either heat or work. But if there's no heat, that means it's only coming in as work, which we can describe as PV work. So if we know the external pressure and the change in volume, we should be able to know the change in internal energy. Now that has its own issues. Now we can go ahead and relate this to what we also found about the changes in internal energy. So in the complete description, if I go ahead and compress the system, I'm putting energy in the system. That can go into one of two places. Either it can take energy to compress systems with repulsive intermolecular forces, as indicated by the Joule-Thomson coefficient. So I can store energy in those intermolecular forces. Or more commonly, I can increase the temperature, so putting thermal energy into the system. So if I'm looking at an ideal system, as we often like starting with, this means that that internal pressure term is zero. So this intermolecular forces volume dependency drops out. And all I'm left with is relating the changes in internal energy to heat capacity. That means I can relate the change in temperature to the change in volume here by relating the work to the increase of temperature inside the system. And this is actually fairly nice, but do notice that we are neglecting this intermolecular forces term. So we're again mostly looking at gases again. But the major idea is by compressing the system, all that energy has to go somewhere, and it goes into increasing the temperature. Now, what we can do is use these equations to help understand what I'd expect to happen to the temperature as I compress the system. How much would the temperature change? Now, to go ahead and do this, what we'll first notice is that we need a expression for that external pressure. So at this point, we're usually looking at one of two cases. Either it could be isochoric, or isobaric, which is relatively straightforward to integrate both sides. But a much more interesting case is going to be looking at reversibility. So under a reversible circumstance, I can go ahead and replace the external pressure with the system pressure. And I do this by dropping the subscript. And now, once I have the pressure referencing the system, now I can use the ideal gas law to go ahead and replace the system pressure with nRT over V. Good old ideal gas expression. Now notice in this case we get a little bit of fun because notice we have temperature dependence on the left, volume dependence on the right. So I can go ahead and move the temperature over, and I'm also going to move over that N and R term. Because by moving over N and R, these should be constant if I'm looking at a closed system. So I've now split everything into three components. I have my constants with the heat capacity, the moles, and the gas constant. I've got my temperature terms, and I've got my volume terms. This is going to make it relatively easy to integrate both sides. Integrating the left, the constants just get pulled outside, and I'm looking at the change in inverse temperature and the change in inverse volume. But when integrating these, we have our good old friends where the change in inverse temperature produces a natural log of final temperature over initial, and same thing with the natural log of the ratio of final and initial volumes. So now we've got something a little bit different than we saw with Charles's law, where instead of a direct relationship in between volume and temperature, We now have this odd log-log relationship. Now we've got to go ahead and rearrange this to make a little bit more sense of it. And for that, we can use some of our log laws. So the first one is I need to remove these prefactors. So I can remove those prefactors by moving them into the exponents. So on the left-hand side, I can move the heat capacity and the gas constant up top. Notice here, I also changed the heat capacity over N to just the molar heat capacity. So now I have the molar heat capacity over the gas constant as the exponent above the temperature. And then on the volume side, notice that originally I had a negative sign. As I pull it up to the exponent, that just causes the ratio of volumes to inverse. So now it's initial over final. Now, one of the biggest reasons we do this is now that I no longer have any prefactors, I can simply just cancel out the natural logs on both sides by raising them to the exponents. What this now lets me deal with is more of a direct inverse relationship in between temperature and volume. But notice now we have something very unexpected because in isobaric conditions, we'd expect these to just be ratio of temperature is equal to ratio of volume. But here, now we have this pesky exponential based on the heat capacities coming in. And this will go ahead and complicate some of the relationships. And the reason why we have this is because in isobaric conditions, we're keeping the pressure constant. But now we have that pressure is also changing, and we don't know how. And so that change in pressure is going to cause this odd behavior in the temperature. Now we can go ahead and rearrange this expression several ways. One of the classic ways is to go ahead and move all of the initial conditions on one side and all the final on the other. This is very similar to what we did with looking at Charles and Boyle's law earlier in looking at gases. But again, notice we have this ratio of molar heat capacity to gas constant coming in. And again, similarly, where we could set this, if we have the same expression for both initial and final, we can just say that volume and temperature relationship is equal to a constant in the same way we did with Boyle's. We can do so here. But again, the biggest difference is we have this exponential, which we now just, because we're going to be using a lot of it, just shorthand that as C. My apologies, we have a lot of C's. In this case, that C just represents that molar isochoric heat capacity, and that does become important later, over the gas constant, with again noting that molar heat capacities and gas constants, as we saw earlier, will have the same units. We can also rearrange this to solve for the final temperature. Now, when we do this, again, we're going to note we have the ratio of volumes to the inverse of C based on the initial temperature. So again, this means that if I go ahead and have a compression, that initial volume is going to be smaller. So I should see as the system compresses, because of the nature of this exponential, we should see the temperature increase. Now, a little bit more direct way of looking at it is looking at these ratios. So again, if I have a compression on this side, I should see an increase in temperature on the other side. Now, in general, this is going to be very important because this will work because that heat capacity, that molar isochoric heat capacity is always going to be greater than R. Because remember, the smallest it can be for a monatomic gas is 1.5 times R. So that's always going to be at its smallest 1.5, at its largest a bit bigger than 3. So as a relationship, we should always see that that temperature change is going to also be greater than the volume change. Because again, imagine if I have the temperature essentially doubling, we'd expect the volume to more than half because it will be magnified through this heat capacity term. Now, one of the reasons why is because we've got this again, this pressure coming in. Note that we're going to have that this temperature change represents the bottom end because this is for a reversible system. If we have an irreversible system, we're putting more energy into the system, so we should see a greater increase in the temperature. In addition, adiabatic compression is going to result in that buildup of pressure in the system because as I'm reversibly compressing the system, I do so by slowly increasing the pressure of the system. And this means that we have to deal with that pesky 3-term case. I'm not looking at a simple relationship of volume and temperature. That pressure is always changing in the background. So if I know how much I'm compressing the system, I know that change in volumes, how can I figure out the change in pressures? Well, we can do so because if I'm looking at an ideal gas, I can insert in the ideal gas law in for the temperature, in for these temperature terms. So now I have a ratio of the whole ideal gases. But note when we do this, we should also see a canceling of these NR terms. So now what we're left with is the ratio of volumes being equivalent to a ratio of volumes times this heat capacity. Now, when we go ahead and do this, you'll notice this is a little bit kind of awkward to work with. So one of the things we're going to want to do is rearrange this expression to be a little bit more easy to work with. We want to move all of our volume terms on one side and all of our pressures terms on the other. Now, when we do this, we can again rewrite our expression. So in this case, we move the heat capacities over to the other side. Now notice we've got a ratio of volume. That way the exponential is only on the smaller term and not on the bigger one. Now we have to go ahead and move all of our volume terms onto the same side. So we're going to do so by moving this PV terms over to the flip side. So we're going to be multiplying both sides by initial pressure volume over final pressure volume. Now this goes ahead and gives us our ratio of pressures, our ratio of volumes, and our ratio of volumes now to this exponential term. Now, the problem is if I'm going to try and combine these two ratios of volumes, which should be able to do, because notice we got final volumes on the bottom, initial volumes on the top. But to do so, they have to share the same denominator in the exponentials. So the classic way we do this is if I'm going to combine these, they both have to have the same denominator in the exponentials. So how we do this is we just say, hey, the exponential on this second volume term is just 1. And I can express this as isochoric heat capacity over isochoric heat capacity. When I do this, I can now combine my two volume terms by just simply adding together the numerators. So now I have my ratio of pressures times the ratio of volumes, but in the numerator, or in the exponent, I now have isochoric heat capacity plus R over the isochoric heat capacity. But this is an ideal gas. Last lecture, uh, several lectures ago, we proved in about 3 different ways that isochoric heat capacity plus R is just the isobaric heat capacity. So what we find is that the ratio of pressures times the ratio of volumes to this ratio of isochoric to isobaric heat capacity will equal 1. Now, because it's awkward to keep saying this ratio of isobaric to isochoric molar heat capacities, we just shorthand this as gamma, where gamma will just represent that ratio of isobaric to isochoric heat capacities. And remember, the isobaric heat capacity should be always greater than the isochoric. So this will always be greater than 1. But it will depend on whether it's a monatomic, a diatomic, or a more complicated gas. So what we can then do is using this expression, rearrange this to relate pressures and volumes. So initial to final. And when we do this, we'll find that the expression is pressure times the volume to this exponential that's always going to be greater than 1. So what we find here is that we'll always require a greater pressure to compress an adiabatic system than for an isothermal. Because remember, for an isothermal, it's just PV equals PV. But now we have this extra term. Now, why the heck does this happen? And the reason why is if I'm looking at an isothermal case, as I compress the system, I go ahead and I keep that temperature constant, so any of the excess energy goes into the surroundings. And that means I prevent that kind of pressure from building up. But so as I expand the system, I'm pulling in energy from the surroundings to essentially keep that volume kind of well expanded. But the problem is that as I go ahead and do this same expansion in an adiabatic, the system cools down, which means it takes a little bit, which will actually affect the ending kind of pressure volume ratio. So again, this gets a little bit kind of complicated when we have to deal with a two-dimensional relationship versus a three-dimensional. So again, when looking at your compressions and expansions, always pay attention. Am I looking at isothermal or adiabatic? Because the equations will be very different in both cases. And again, remember, in both of these cases, we're looking at at reversible. And that this can indeed look a little bit different if we're looking at a non-reversible case. So, so far we've looked at a lot of different ways to do expansions and compressions, and the equation should be kind of buzzing in your brain from now. So next time, we're going to take a little bit of break on new material and try and review everything we've learned so far about expansions and compressions of both real and ideal systems. Until then, take care.